Hello, welcome everybody to the 3D scanning and motion capture lecture. Today we're going to talk about non-rigid tracking and the reconstruction. Specifically, the reconstruction will be the focus here. In the last lecture, we've talked mostly about mesh deformations. We've talked about how, well, mostly in computer graphics, in geometric modeling, how you can essentially take a mesh, have a bunch of handles on those meshes, and move the handles around, and then we can basically apply the deformations based on the handle constraints. And this is done via applying some priors. And one of these priors we have looked at was as rigid as possible Arab, which is a very popular one. And the core idea of most of these approaches is that you basically have a fitting term here that's given by the handles, and you have a regularization term. With Arab, this is basically given via this local rigidity constraint. And the idea is that both of these terms, they kind of compete against each other, whereas you say, hey, you want to stick close to the handle locations, and the Arab term tries to distribute the deformations in this as rigid as possible way on the rest of the mesh. Another very important deformation prior we've looked at was embedded deformations. Very similar idea than Arab. But the only difference in this ED term was that instead of having this rotation matrix here, we're having a 3x3 matrix, which is not hard constrained to be a rotation, but rather to be soft constrained to be a rotation. So there's a specific rotation term that says, please make this matrix as similar as possible to a rotation matrix, but it can't deviate from it. And that's kind of the key difference to Arab. And then, basically the core ideas in all of these regularization terms here, that if you have a user edit, you move this vertex from here to here. If you just take the connectivity, you would get this one. If you would just take the regularization term with ED, you would essentially get something like this, right? So everything would move along the same way. And now you're making sure that these M's here, these M matrices should stay close to rotations, then you're getting something like this here. And again, all of these are nonlinear optimization problems that you can solve, for instance, with Levenberg-Marquardt, which we have looked at in the past. Now, the key differences, I briefly mentioned it. So Arab, right, these are hard constraints for rotations, ED are soft constraints for rotations. Key difference is Arab has 3 unknowns per local vertex. Sorry, it has 3 unknowns for this matrix because it has 3 angles for the matrix. So it has 6 unknowns per vertex, 3 for the rotation, 3 for the translation. And can be very efficiently optimized with the flip-flop optimization. So you can basically locally solve an SVD and then alternate propagating those changes globally. Okay, embedded deformations, similar idea, except that now we have soft constraints for rotations. We have 9 unknowns per local matrix. So we have 9 for the matrix, 3 for the translation, sums up to 12 unknowns per vertex. It's a little bit harder to optimize. There's no such nice alternating scheme. Yeah, it's a little bit more annoying to solve, but in practice, it allows a little bit for more flexibility. So it depends a little bit what kind of deformations you want to encourage and what behavior you want to have. Okay, lastly, we talked about deformation proxies. So basically, rather than computing these terms that we have just seen on the mesh itself, you can compute them on cages, grids, skeletons, and so on. And then one specific thing we talked about was deformation graphs. That's very commonly used, and we're going to follow up on this one today because we need it for a few non-rigid reconstruction methods, actually, right? Yeah, so what we know now is, right, we know how to deform a mesh, we know how these priors are being applied, and we know in principle how to solve those priors as well. And one of the last things we looked at was this non-rigid tracking approach. So there, we can use those ideas now by first reconstructing a template, and then essentially doing a non-rigid ICP on this template. So once this template is reconstructed here, so this is kind of a static reconstruction. It's not perfectly static, but it's pretty close to being static. And then we can apply some non-rigid deformation tracking here by applying all of these things that we have just learned. Except the only difference was that, these data terms now, they don't come from user-specified handles, but rather they come from data terms. For instance, with a non-rigid ICP, where you're having point-to-point, point-to-plane errors, or even color consistency terms. And yeah, and this regularization term is essentially well, it is as rigid as possible, and it is jointly optimized along with the data terms. And then this is a non-rigid optimization, and then you can do this non-rigid tracking. So this is where we stopped in the last lecture. And one of the things that we have discussed already was that with these methods, you have to basically have this two-step approach now. So now we have to first reconstruct the template, and then we can track the template over time. I'm not saying that's a bad idea, right? Many times actually people do this. Specifically, we'll see this later, that for faces or bodies, people actually have those templates already pre-computed. It's not like an exact template of one person, but in principle, the idea holds that you have a template pre-computed, and then you want to more or less track this template over time. But in principle, one thing, if you're looking at literature like this, you will often see these kind of energy formulations. These energy formulations will obviously change depending on what method exactly you're using, what features you're using, what regularization terms you're using. But the high-level ideas, I think, are really important, that essentially we have kind of these energy terms that we're trying to minimize in order to figure out our non-rigid deformations and eventually how to track the objects over time. Okay, so let's continue. And today we want to talk about the reconstruction. So if we remember, if we're going one step back, forget about for 1 second for the non-rigid part. If we're going back to the Kinect Fusion pipeline, this is a pipeline that all of these volumetric fusion papers did, right? So this is what we have done for rigid surfaces. And what we want to do now is we want to kind of fit these puzzles together. So again, remember, for rigid surfaces, the idea was we're getting an input depth map, we're pre-processing this depth map, we filter it, bilateral filter, something like that. And what we do is we have a model on the other hand. From this model, we're raycasting the current frame. And then we're doing an ICP between the pre-processed depth map and the raycasted depth map. And that one gives us a camera pose that we're getting with an ICP, for instance. And based on the 6th camera pose, we're now integrating the current depth map into the current model and updating it accordingly. And then we're continuing this every frame, right? So this is the core idea. What rigid surface reconstruction with volumetric fusion and Kinect Fusion style methods are doing. And that is essentially where we want to continue now, except now we have non-rigid tracking, right? So basically the only thing in this whole pipeline that is going to change is this part here. So instead of doing a camera pose estimation with the 6th, we now have a camera pose estimation and a deformation estimation, right? So we have to do two things here at the same time. And but in principle, then it's very similar to the things that we have seen before, right? Like before, we have seen how we can track a template non-rigidly, and basically between two adjacent frames in the input sequence, we're gonna now go ahead and track the template and do the reconstruction with the non-rigid deformation parameters accordingly afterwards, right? And this is essentially what dynamic surface reconstruction is doing. So there's a little bit of an intricacy that we have to talk about. So one idea here is we say, well, we have kind of a sign distance field. And this sign distance field, what we can do from it, we can extract some sort of surface out of it, right? So for instance, you can running a marching cubes or something like this. Based on the extracted surface, we can find correspondences with the current observations that we're getting from the input data, right? In principle, that's very similar to the rigid reconstruction. The only difference is now instead of raycasting it, because raycasting is kind of hard for non-rigids, what we're doing is we're deforming the sign distance field according to our deformation warp that we estimated. We then running a marching cubes to get a surface. Based on that surface, we're finding correspondences with respect to the input depth map. And based on that, we basically apply a non-rigid deformation optimizer, non-rigid ICP, between what we have seen in the input depth map and between whatever we have seen in the extracted isosurface. That gives us an optimization that tells us how to deform the whole thing based on the current frame. And then we update the current deformations. And based on that, we then fuse the current depth map into the canonical volume, pretty much following volumetric fusion as it's done on rigids, right? So there's two key things to consider here, right? The one key thing is instead of operating on the original SDF, we actually using the previously estimated warp field of the SDF, warp it to the previous frame. Then we're extracting a triangle mesh. Then we're finding correspondences with respect to the current observation of the input depth map. That's the ICP correspondence finding part. And then we're applying a non-rigid optimization that tells us how do we have to, what's the non-rigid deformation parameters between that mesh we've just extracted from the volume and the respective depth input. And based on that, we update our deformation parameters. And from there, we can integrate the current depth map into the current volume, right? So basically, this thing here is the non-rigid ICP. This here is the data extraction from the volume. Instead of a raycast, here we're using a marching cubes because raycasting non-rigidity is not so straightforward. And this is the pipeline then what we can use for non-rigid tracking plus volumetric fusion, basically, right? And this is what this I would say it's a pretty seminal paper, the dynamic fusion work by Richard Newcomb. So the idea is essentially that they wanted to expand Kinect fusion to non-rigid scenes or to non-rigid objects. And this is exactly what this paper is doing. And I want to talk about a few details there that you just get a bit of a rough idea like how this thing works. But all of the things that are being used in this paper, we have already talked about in this lecture. So this is kind of the T0 step when you get the initial depth map. This initial depth map is being integrated in this canonical volume. Then you get another frame here. At this next frame, you basically have an estimate of the deformation parameters based on non-rigid ICP between what we had here and what we are seeing in the depth frame here. Then we're integrating the current depth map here. Then we're getting an update, and then we're continuing and doing this for every frame, right? So, few details here. So the idea here is this is essentially using for the template warping here between two frames for the non-rigid ICP. They're essentially using an embedded deformation regularizer. They're using a they're using a regular volumetric grid that is like just large enough to capture a single person. For the embedded deformation, they're using a deformation graph, and that deformation graph is a sparsified version of the current representation. So they don't go into that much detail, but basically the number of deformation graph nodes that they're using determines how many degrees of freedom they can handle. That determines a little bit of how stable it is. So basically, if you have fewer degrees of freedom, it's going to be more stable, but you're going to lose a lot of deformation detail. And also, the fewer deformation degrees that you have, the more costly it is to compute, because the larger the deformation graph, the slower the whole thing gets, because the nonlinear optimization is becoming more and more complicated. Right? Okay. Again, same example here, right? Initial frame here. Then you have the depth maps for all the frames. And then here they have the deformation nodes. And what's important is they can always extract the model in the canonical undeformed frame, because whenever they're doing the volumetric integration, it's in this undeformed canonical pose. And then when they're getting a new depth map, they're basically updating the deformation estimates from this canonical pose to the current depth map. Based on that, they can then warp the canonical model into the current frame. And based on that, they can then reintegrate the current frame's depth map in order to update the model. And this is being done online in an incremental fashion. And this is kind of a reconstructed normal here that you're seeing at the end of the day. Okay, so maybe to quickly summarize the whole thing here. So the core idea is it's a deformation graph based on ED. It uses a non-rigid ICP between the current frame and the canonical model. It does volumetric fusion once the deformation parameters are estimated. It updates the current model. And this is done by several steps per frame, right? So for each frame, you take the current depth map, you extract the depth map of the current warped model using marching cubes. I've mentioned this before. Then you align the input frame with the extracted frame using the dense non-rigid ICP. We know now how that works, right? That's very similar to the things we've learned in the last lectures. That's an optimization problem where you have to find the optimal unknowns for the deformation graph deformation parameters. Once you have those ones, you integrate the current frame into the canonical model, and then you go to the next frame, right? And then you iterate this until you finish your sequence, okay? And I think this was very cool. This dynamic fusion paper came out 2015. so like a few years ago now. But the nice thing about this paper basically is that this actually run pretty much in real time. And I mean, sure, they could run it for only one model, but this was, or I would say it's still pretty remarkable, like what you can do with that. And so I want to quickly show the video here. So this is the video that they had. And here you see the reconstruction. You see the live reconstruction, smiling face is one sequence that they had. And you see here, always, you see the live input map, you see the live model output, and on the bottom left, you see the canonical SDF, how it would look like when you projected everything back in the base frame. Okay, and that's what they're getting. So then they can extract, of course, the mesh in the canonical frame. They can also extract the mesh at every pose. Okay, they have a few more sequences here. So I think this is a pretty remarkable sequence of this little girl here, because there's a lot of fine scale detail. Even if you look at the hands, they're actually pretty well reconstructed here. Another sequence here. So this is also a very, very important sequence, very critical, or very difficult sequence to do. Another sequence. And again, what's always interesting is you basically see here, you see here the input depth map, right? And you see how the canonical representation is growing as you're getting more information. Right, so you see here the bottom part just came through when the rest of this came. Okay, so this is essentially the pipeline for dynamic surface reconstruction. And one of the things here to say is, if you have very fast motion, this non-rigid ICP is kind of the big weakness of the whole pipeline, right? Or I wouldn't say weakness, but it's the biggest challenge, right? Because one thing you have here is you have this finding correspondence stage that are used to optimize for deformation. So one question is always, is the surface moving? Or is there a deformation, right? Or is there just new surface stuff coming to it? And this is very tricky actually to disambiguate. And so one idea there is basically to augment the correspondence finding problem and make the non-rigid ICP more robust. And this is this idea of this volume deform paper, which is essentially a follow-up of the dynamic fusion. And here the idea is to simplify the pipeline a little bit. So first of all, there's a regular deformation grid rather than these arbitrary nodes. That makes the optimization a bit more stable. This is based on an Arab term, which is also a little bit easier to optimize, so this makes it a little bit faster. And the most important thing is what you can do now is, instead of just using the dense depth map, you can go ahead and have sparse SIFT matches between the frames that you're getting as input and the respective canonical model. So basically the canonical model stores a bunch of SIFT key points in the canonical pos, and these ones can then be used in order to match them with the current frame, right? And then the pipeline changes a little bit here. So for each frame, now you're taking the depth frame as input. Again, you're still extracting the depth from the current warp model using marching cubes. And then you align the input frame with the extracted frame using a dense non-rigid ICP. But this part here basically is now augmented with SIFT matches, so you have more robust matching parameters than you had before. Okay, and this is how that one looks like. And you have seen these sequences already, but basically this is now a little bit more robust, but it's the same idea, right? And now you know what all of these things mean here. So now we have here the color input, right? We have here the live reconstruction. We have the canonical model here respectively. You have the depth input. You have the respective warped reconstruction. That is basically this canonical model, quote unquote, multiplied with the deformation parameters to the current frame. Yeah, and here you can see it's very nice that it can handle actually very complicated motion right now and very complicated surfaces without using a specific surface prior. Okay, so yeah, there's a bunch of these key differences, right? So there's a high resolution deformation field that is on a regular grid, optimized with RUP. It's based on a bunch of sparse SIFT correspondences, and that these global anchors, they stabilize the whole thing a lot better. And as a result, what's kind of interesting is, depending on this grid resolution, you can actually optimize for the RGB textures at the same time, right? So this is basically 60 grid key points. That's a relatively low resolution for the deformation graph. And then if you're upping the deformation graph here, basically you're getting a higher and higher texture resolution, depending on how much compute basically you can afford to get the whole thing running in real time. Okay, there's an example actually how much these points matter. So especially when you have planar surfaces, right? You know that an ICP, generally speaking, has some trouble when you're running planar surfaces. Then the SIFT key points actually make quite a difference, and then you can basically get significantly better tracking results here. See here at some point the no SIFT version fails. Okay, and there's been a couple of follow-up work on this one, and this is not by no means the end of the line. You still see that even these motions here are still relatively limited and relatively slow. So there's a couple of really cool follow-up papers. So there's this real-time geometry albedo and motion reconstruction work by Guo et al. And the idea here is basically, well, it's not just doing an optimization based on the surface, but it's also optimizing the albedo of the representation. So it's trying to factor out the lighting of the RGB and then get better dense matches on the lighting. So rather than just using a bunch of sparse SIFT correspondences, the idea would be that you can also have a dense color term. But since a dense color term is not so straightforward, this works a lot better when you're factoring out the albedo. We'll later talk a little bit about lighting and materials, but all I'm trying to say here is they're trying to get rid of view-dependent effects, basically, by getting the albedo, and because of that, they can get better frame-to-frame tracking and alignment, respectively. Okay, the key idea here is also they're using also an embedded deformation model with a deformation graph. They have a non-rigid ICP. And again, the key difference here is now they're using dense color terms, and they use this illumination correction for the color terms. We'll talk about it later how this works in detail. But the key difference right now, I think what's important to know is rather than just using a bunch of sparse SIFT key points at a few locations, this is now a dense color term that is being applied on the entirety of the surface, right? And because of that, they're getting much more stable tracking at the end of the day. But the rest of the pipeline is pretty similar, right? Again, you have a canonical frame here, you have frame T-1, and then you do joint motion and lighting optimization by using the RGBD input frame. You're updating the frame, mapping it back canonical frame, and so on. So I also want to show this video. I know I'm showing a lot of videos, but I'm generally speaking pretty excited about this stuff because it's pretty remarkable how well, it's not fully working yet, but it's how much this has progressed. So here's the video. Let me play this one too. Okay, so, and you can see that this is already pretty cool, right? So they have geometry, they have a reconstructed texture on top of it, and that texture also looks already pretty good. And in their case, the texture is really critical because they use the textured model here for the actual surface tracking. Okay, they have a few more sequences. And yeah, I think it's kind of remarkable. So they can do the relighting. Let's ignore the relighting part for now. Again, we're going to talk about this one later. But I want to highlight how sharp the textures actually look like. And again, for them, it's really important to get these textures because for them, it's kind of the main part of the tracking term because they're using this dense photometric reprojection term. It's kind of like what BodyFusion is doing for rigids, but they just have to optimize a much harder optimization problem here, right? Because they have this non-rigid motion that you have to think about. Okay, there's a few more sequences. So yeah, the authors here got very creative in creating some moving sequences. Okay, so one thing I feel what's kind of interesting, again, the texture is kind of the main thing here to look at. So this is the input RGB on the top left, right? This one here. And if you're comparing it to the previous approaches, this was dynamic fusion, this was volume deform, they got very blurry textures. So volume deform looked a bit better than dynamic fusion, again, because they use SIFT key points. But this approach is a lot better now because they're using the dense alignment, and because of this dense alignment, they're getting actually pretty good reconstructions here at the end of the day. Okay, so I'm just gonna go further through kind of history, how this evolved. One of the next, I would say, pretty remarkable papers that came out was this Fusion 4D. They built up on a very similar level, but now they use essentially they have a couple of ways to deal to some degree with topology changes, and they also they also used better depth data, similar to the depth data we have seen before, and then they get also better reconstructions at the end of the day. So this was the paper by Microsoft Research. There were a lot of people involved, so you can imagine it's quite a complicated system. So right, but again, they have more cameras now, right? So they're using I think they're using eight of these camera pods here. But you can see like how the whole field is in a sense maturing, right? So now you can actually get pretty good dynamic reconstruction already. Again, admittedly, they're using 8 cameras here, but still the reconstruction I think is kind of cool. And because they have pretty good data, they can actually do fairly complicated sequences. So this is what they have doing here. They have these kind of dancing sequences. And so on. Yeah, I think this is a very impressive sequence because that's basically doing a topology change on the jacket. So this is something none of the previous methods could handle. They have a couple of nice ways to detect these things, and then they just split the surfaces there accordingly. So also the hair is kind of an interesting one, right? It's a very difficult part of the reconstruction here. Here again, they have a combination of multiple objects at the same time. Yeah, now this is basically a comparison to the previous methods. By the way, whenever you're doing a research paper on your own, you always have to have a conversion like this. Okay, but I think I want to talk very briefly a bit about some of the more details here, right? So they basically using this eight depth cameras. They have 8 stereo cameras, meaning they have a total of 16 IR cameras going on here with the active stereo setup. And one thing they're doing is they're using key volumes, meaning that they don't have a single canonical volume, but they have multiple canonical volumes. And because of that, they can do these topology changes. So when they detect it, they basically spawn a new key volume. And yeah, I think it's a pretty cool paper, and you can see how far you can engineer these systems. And basically, Microsoft started then marketing this one as Holoportation afterwards. So I wanted to show you this video also, because I think it's kind of a very cool video here. So then they basically pitched this as, okay, how can you create content for your AR devices? And specifically, Microsoft has the HoloLens, right? So this is one of their flagship projects in this area. And now basically they had this reconstruction setup, right? So they have these cameras here everywhere. So again, this is a costly setup, right? This is not something you can easily do. They have these HoloLenses here, but just to clarify, this is more like a marketing video. These HoloLenses are not actually active here. They're just using them for fun. But what's real is the reconstruction you see here in the background. And I think that's kind of remarkable. And here's basically the full reconstruction of a duplicate setup from a different room. And then he's kind of virtually inserted into that video stream here. And I think that is kind of remarkable. So that's very cool what you can do then basically. So you see a little bit how the research goes from like, small step-by-step, research advances to actually having a full setup with like multiple cameras and so on that you can then use in order to reconstruction, and basically with that create the content respectively for, let's say, an AR device like the HoloLens. Okay. Yeah, I guess I can still run the rest of the video because I think it's kind of cool. You see here how he's duplicating himself. And yeah, you see basically, this is all basically just non-rigid reconstruction, all the stuff we have just seen. Now they have, here you see the second setup they built in this little corner here. It's basically the same setup, and then they have the little kid here that is being remote projected into that target here. And I think it's kind of a cool video. And yeah, then the actual footage in the HoloLens looks something like this here. Okay, so I wanted to highlight a few follow-up work still. This motion to fusion is kind of a cool follow-up work. This is the same group. Also want to quickly show a short video here. And the idea of that one is basically that they now kind of they want to get it faster. Like one of the big problems they had in the previous videos was that it was too slow to run it on commodity devices. And here you see already they have depth cameras at the top here that are a little bit more lightweight than using these super expensive active stereo setups that they build custom. And then they added the textures, of course. They looked a little bit better. And they get pretty good reconstructions now of fastener motion. This is one of the deal that they had in this work. Okay, and then they're showing the reconstruction pipeline. Again, it's very similar to what we've seen before. They're using basically key volumes as well. And then they having a two-way non-rigid alignment and fusion between those key volumes. So let me actually explain this maybe a little bit better. So they basically have the depth data, the color data. They have learned 3D correspondences. Now, this is one of the first papers where they start using deep learning right now. Sorry, I think they're using random forest. I don't remember it, but this is one of the first ones where they're using actually learned data in order to learn the correspondences rather than using handcrafted ones. I think this was one of the first ones using deep learning. They had a time when they used random forests, but you see 2017. Nowadays, in like 2022, you would all use deep learn features. I'll get to this in a second, what this means. And one of the cool things what they had this two-way non-rigid alignment. So basically, the idea is they're mapping from the data to the reference and from the reference to the data. And by doing this simultaneously, with this forward and backward mapping, they have the cycle and the deformation mapping. And because of that, they're getting more robust correspondences. Another thing they do is actually, which I find cool, they have kind of a detail layer. So they decouple the rendering from the tracking, meaning they have a 2.5D volume to capture the high frequency details that can be lost during the matching process, right? And I think that's kind of nice. Because of that, they're getting these like super high resolution local details. Okay, I want to show one more paper along these lines. This is called LookinGood. And the idea there is kind of interesting. So the reason why I want to show this, so they don't have a novel contribution in the sense of the tracking, but what they do is they basically now use, this is one of the first papers where they say, okay, they've tried now for several papers really hard to get better reconstructions, but the problem at some point was the reconstructions didn't get a whole lot better, but maybe the reconstruction wasn't the issue. Maybe they should just fix the rendering, and they use the neural network as a rendering architecture. So they basically have some reconstruction, and then they're using a deep network to get better rendering outputs from the kind of imperfect reconstructions that they had. And I think that was kind of a cool idea. The reason why I'm mentioning it, because we'll later talk a little bit more about neural rendering and how that helps possibly the reconstructions. So I want to show that video here as well, because that's kind of interesting. So play actually. Hope it plays. Yeah. Okay. So here the idea is they basically have a capture setup, and then they can use the neural network in order to get real-time performance, where they're patching up the imperfect reconstructions with the neural rendering network to get better visual results at the end. And this is kind of what they're getting here. And I think that looks kind of cool. And one thing you can already see now, this is a paper that was published in 2018. So we're getting closer and closer to the current year. And yeah, I think that's kind of interesting, because they now say, okay, look, we're okay with our reconstruction quality. Now they're going to use neural rendering to get better re-renderings. And that's something, again, I want to mention a little bit later how that works. I don't want to make it a deep learning lecture. We have our intro deep learning, of course, at TUM, but I wanted to show how kind of these different, methodologies kind of work together very well. Okay, there's one last paper I wanted to mention in this case. There's this DeepDeform paper. This is a paper from our group. So here the idea was basically we want to use full depth neural networks now to learn correspondences between neural networks. So kind of the high level idea is there's a data set. In this data set, there's a bunch of sparse annotations. There's RGBD capture. And from this capture here, there can be reconstructions. And from these reconstructions, we can basically run like very, very strong data-driven priors in order to get better correspondences for our non-rigid ICP in all of these dynamic fusion pipelines or general non-rigid reconstruction pipelines. Okay, I want to quickly show that video because I think that's also kind of interesting. So here the idea is basically, well, existing approaches, they only work for relatively slow motion, like this is basically the dynamic fusion work. And as soon as you have like more complicated motions or so, this kind of stuff doesn't work that well anymore. And so the idea is basically we need better correspondences. Same thing. Like if you're moving too fast. By the way, this is how this stuff looks like when it fails. This is when dynamic fusion fails. And then the idea is basically now we want to learn correspondences, and based on these learned correspondences, we can make the non-rigid ICP more robust. and based on that, it can deal with more complicated sequences. And this is kind of the final result here of this paper that can deal with these faster motions. Okay. So the main core idea, if you want to work on these kind of areas, you can check out this data set. So this has semi-supervised annotations, meaning that there's a bunch of sparse annotations, and by the sparse annotations, there can be the correspondence forward propagation, and then there's a heat map network that is being trained, and based on this heat map network, there can be better correspondences learned. This is kind of how the data set here is being created. So this is an RGBD data set that is captured with a structure sensor. This captures RGB and RGBD. And then the reason why, again, it's semi-supervised is because there's going to be first a segmentation mask being applied on a bunch of frames, right? So we know the object of interest that should be tracked. Then there's sparse correspondences being annotated, and based on these sparse correspondences, there could be a dense alignment based on a non-rigid template alignment. So as a non-rigid ICP is basically being run with these ground truth annotations. And then the data set, this is the semi-supervised part, basically based on these sequences. We have 400 of these ones, right? Based on these sequences, the data set can then augment all the missing points. And this is what's being done here. Now there's a network that is being trained on matching. And this network architecture looks something like this. It's basically a Siamese architecture that takes as input 2 encoders. These encoders take RGBD frames as input, so it's a total of 4 channels, basically. These encoders between the source and target frames, they share weights. There's a bottleneck layer, skip connections. There's a decoder and a visibility output. The visibility output tells us for that query point, is there actually a target, yes or no? That's a binary cross entropy loss. And this is how these correspondences that are being trained look like then in practice. So you get pretty stable non-rigid correspondences in these respective output predictions. And you see this can now be, the correspondences are pretty robust, right? So this is a network that is basically run a couple of times here. Of course, it runs a lot better than previous matching methods here. That's kind of an evaluation that's being done. Yeah, this is like previous matching methods for for rigids. Actually, they don't work that well for various reasons. Okay, and then here's the interesting part, is basically the full reconstruction right now. Now we're gonna take these correspondences in the depth input in the ICP part. The current reference, so the current frame is being basically sampled. The network is run for each of these points. Then you get correspondence to the reference image, and then you can get a reconstruction of the final output here. A few more reconstructions here. That's the reconstruction evaluation against the respective baselines. So again, when you do an academic paper, you have to make sure you're better basically on every axis here, otherwise it's going to be tough to publish it. Okay. With that, I would like to do a quick summary here. So today we've talked about non-rigid tracking with non-rigid reconstruction. So there are several degrees of freedom per vertex in the tracking. But you don't get any drift, which is kind of interesting. So if you always track with respect to a certain template and you apply the regularization term with respect to this template, that means that there's no drift, right? Because the regularizer is not going away. And if you remove the correspondences, the mesh would basically snap back in this original template position. Now, with non-rigid reconstruction, it's a little bit more complicated because you still have several degrees of freedom per vertex, but it always does basically template tracking with respect to the previous frame and then quote-unquote update the template mesh accordingly. And because of that, one big challenge of this non-rigid reconstruction is that it accumulates drift. So if the tracking is wrong at some point, then the surface integration will be wrong and then everything is kind of falling apart. One thing is you can reduce this by using new key volumes every n frames. So you basically have multiple template tracks. This is what this Fusion 4D and all the follow-up papers were using, what I showed you at the end. But it's still tricky, right? Basically, the challenge is you always have this issue is it a surface motion or is it a new surface, right? And that's not so easy to figure out. So generally speaking, it's super challenging. It's often under constraint, particularly from a single depth image. From a single RGB image, I'm not even talking about single RGB image at this point. Even from a single depth image, it's pretty difficult. RGB only tracking does work to some degree. You can find correspondences as long as you have a stable template. You can do this to some degree. But joint reconstruction with RGB only is even today is not so much of a thing. So it's still difficult. So you would have to do some sort of non-rigid bundle adjustment or non-rigid multi-view stereo. So there's works like that, but these works are not at the level of quality yet that could be used for like a full-scale reconstruction here. Because I mean, one challenge, generally speaking, is you need to hallucinate a lot of missing data through regularization. Neural networks can do this to some degree. You know, if you're interested in these areas, you want to basically combine these ideas here that we're talking with this lecture and what we're doing with deep learning. Some of them I might mention in the next few lectures. But basically, in practice, you don't always have so many correspondences for the deformations, and then it often is an under-constraint problem if you regularize it. Okay, so I want to quickly give a high-level, maybe a high-level view again of this area here. So when we're talking about dynamic 3D capture, we kind of have three types of dynamic captures, right? We have free-form tracking. Free-form tracking is the thing we've done in the last lecture. Like it's an offline template reconstruction and then online tracking. That's what we've talked about in the last lecture. In today's lecture, we've talked about free-form reconstruction, like joint reconstruction and tracking. And then there's going to be things like domain-specific tracking. Like, for instance, you know it's a human body, it's a human hand, or it's a face, or something similar, right? So this is basically giving you even more regularization priors and domain-specific knowledge that helps you to over-constrain the problem more. And this is something we haven't talked about, and this is what we're gonna talk about like in the remaining part of this lecture and also specifically in the next 1 or 2 lectures actually, right? But I want you to understand that there's different application scenarios and different methodologies that can target each other, right? So here the advantage, right, is this one works on everything, but it's the hardest to do. This one works in pre-constructed template, but works still on everything. And this one works only on specifics, but it's more robust in a sense it doesn't fail so much. So this is kind of the, you know, like, depending on where you stand and what methods are the right ones right now. Okay, I wanted to show one cool work for domain-specific things before we're ending today. BodyFusion is a very interesting method. So I just want to show you how you can combine these ideas from the generic fusion methods to domain-specific methods. And the idea of this BodyFusion methods is basically you have a skeleton. The skeleton gives you the deformation prior. And then you do a volumetric fusion on top of the skeleton, right? So it looks something like this. Here we have a skeleton. We have a tracking. the tracking is relative to the skeleton, and then you do a fusion into a volume that is rigged by that skeleton. So this is a very simple idea, right? So you basically now have a deformation prior of a skeleton embedded into a volumetric fusion method. It's very similar to what we've seen in the last method when we had like RUP on skeletons. This one is basically very similar, except now it's being done in a live interactive fusion method. And I wanted to also show you some results here, because I think that's also a very cool method actually. Looks something like this. So now they're basically tracking the skeleton, right? And then they can do much more complicated and faster motions. But again, this only works now for the human because that has to be rigged with respect to the skeleton here. And I think that looks pretty cool, right? So they can get pretty good results. But again, note that they have a very stable prior with the skeleton that models their deformations for them. Another sequence here. And yeah, so this is the very first glimpse into what you can do with domain-specific priors. In the next lecture, we're going to go into this a little bit further. The core idea of these methods is going to be we have a smaller number of deformation parameters. It's actually significantly smaller than the number of vertices or points you want to integrate. And then the idea is based on these basis functions, you want to apply some skinning and integrate the respective data in the canonical volume. So this is basically what people do for hands, faces, and bodies. And specifically for these ones, we're going to look into this a little bit more. So with that, today was a little bit of a shorter lecture, but we still have a few administrative things. I wanted to still give you some reading homework. So one of the things I would like you to do is have a look at the dynamic fusion paper. Most of the stuff you should have gotten from today's lecture, but I want you to have a look at it and you can see how this is basically written down. I also want you to have a look at the DeepDeform paper, how you can basically integrate like deep learning methods possibly with correspondence finding in non-linear reconstructions. And then yeah, next time we're going to continue with domain specifics, and that's going to be also, I think, super exciting because then we can do more things on faces, bodies, and hands specifically. And with that, thanks a lot for tuning in. See you all next week. Bye-bye.